Okay, so again, today we'll start with a tutorial problem. Okay, so today we have one problem. Okay, and there are 3 parts. Okay, so again, you can find this file on Blackboard. So I would like you to spend a few minutes to look at part A first. Okay. Okay, so this question, I just want you to practice how to do gradient in spherical coordinates, right? So this is a function, a scalar function, right? So depending on r, theta, phi. So as you can see, it actually only depends on r and theta, but not phi. Okay. So this function, okay, so as you will learn sooner or later in 2041, you understand that this is the electric potential for a point dipole. Okay. But it doesn't matter at this point, right? So this is, I just tell you that this is a scalar function, right? So, and then if I have this electric potential for this point dipole, okay, so by definition, right? So finding the electric field is to take the gradient of this V and add and with the negative sign, okay. So all I want you to do is to take the gradient of this function, okay. Doesn't matter whether you know that this is actually referring to the potential function of this dipole. Okay. So take the gradient, right? So and then you show that the minus of the gradient is written like this. Okay. So everything is expressed in spherical coordinates. Okay. Okay. So let me just write down the answer. So essentially, what you just need to recall is that the gradient formula for the spherical coordinate, right? So in spherical coordinates, right? So the gradient of some function, right, is written like this, right? Just applying the formula. Okay, so this is just a formula that you have seen in the last lecture, right? So nothing more than that. Okay. So then we need to take care of partial V, partial R, right? Partial V, partial theta, and partial V, partial phi. So partial V, partial R, right, would be, right, just look at this function and take the derivative only for R, right? So and then what you have is this. Okay. And then let's also do partial V, partial theta. So again, look at this function, right? Just take derivative for theta. Yes, thank you. I'll use it later. Right, you have this cosine, and after derivative is sine. Okay. So and partial V, partial phi, of course, is just 0, right? Because this function does not depend on phi at all. Okay. So that's why the gradient of V is given by this, okay. I have already skipped one step and take out the common factor. Okay, so this is the gradient of V. So now the question actually want you to find the minus of the gradient, right? So then the minus of gradient is this. Right? So then that proves this result here. Okay. So this is the electric field. Okay, so I understand that at this point, I think you have learned that if I have a dipole, right? So here you have learned that the electric field along the axis. Okay, you have also learned the electric field along this middle plane, right? So, but if you want to find the electric field for all space, okay, the condition is that this actually only works when you are far away from the dipole. Okay, so then the electric field at any point is given by this. Okay. So you can see that it has an R component and a theta component. Okay. So if I draw the field pattern, it looks something like this, right? So basically you just imagine that you have a positive charge here, negative charge here, and then at this, for example, at this point, right, the E field point this way. Okay. If you are here, then the E field point this way. If here, E field point this way. Okay. So this E field, right, will always have two components. Okay, one is the component along the R head direction. Okay, so and the other is the component along the theta head direction. Okay. So but it does not have any phi head component, right? So the electric field really just goes along this plane when I particularly consider the plane of this screen, right? So, but of course, if you ask, what about if I pick a point, because this is really a three-dimensional a problem, right? So if you pick a point that is kind of outside of the screen, right? So what would you have, right? So you just imagine that you rotate this whole pattern like this. So essentially, this pattern is basically just imagine this is really like a magnet, right? A magnet with this north pole and south pole, right? So, but for magnet, we will be talking about magnetic field, right? So, but the pattern is actually the same. Here, of course, we are just talking about electric field. But anyway, I have a function, right? Taking the gradient give you some vector field. Okay, so then the next part I want you to do is to do the line integral for this field. Okay, so in particular, I prepare two paths. Okay, so you can see that. So this is a spherical surface. Okay, just a virtual surface, right? So you just imagine that the field is everywhere, right? So and this sphere is again, of course, it's a sphere centered at the origin and with some radius r. Okay, so and then I pick two paths, right? So one is the red path, which is this closed circle, right? So which is at a constant latitude, right? If you think of this as the Earth, right? So this one is at a constant latitude line, right? So and then the other path, which is the blue one, is the one that go from the north pole of the Earth all the way along the surface of the Earth, right? So down to the south pole of the Earth. So this is a semicircle, right? So and it basically goes along a lines of longitude, right? So So I want you to try to do the line integral over this path, right? And also this path. So in fact, these two paths are the two paths that are very convenient to deal with in spherical coordinates. Okay, so you will notice that, right? So let me do the blue one first. So if you walk along the blue path, right, so you can see that only one of your coordinate is changing, right? So your R coordinate is not changing because you're always at the surface of the Earth. So your R coordinate is always capital R, right? And also your phi coordinates, a smoother angle is also not changing, right? So and what the only coordinate that is changing is the polar angle theta, right? So now we call the expression of dr, okay, in spherical coordinate. Okay, so dr is given by dr r hat plus r d theta hat plus r sine theta d phi hat, right? So this is from your last set of lecture notes. So this is the dr for in spherical coordinate. Okay. So now because of the fact that your r coordinates and your phi coordinates are not changing when you're walking along this blue path, right? So then that means your dr, this term is 0, and this term is also 0. Okay. So if I try to, let me try to draw the cross section of this Earth, right? So if I try to draw the cross section, right? So then this is the path that I'm taking, right? So this is theta, right? So you're walking in this direction, okay? So then your dr is that after your theta coordinate has changed by some small amount d phi, d theta, right? So then your the step that you make is indicated by this small arrow, right, which is r d theta hat. Okay. Moreover, the r is always fixed at capital R, right? So in this case, so that's why this small r really is capital R. Okay. So that's why if I'm walking through the line integral over this blue path, okay, so then my dr is this capital R d theta hat, right? So that's why the line integral is written like this. Okay. So it's an integral over data. So let's take care of E dot data head a little bit later, but let's take care of the integration limit first. Okay. So because this just one variable is changing, right? The other two are not changing. So there's even actually no need to do parameterization at all, right? So you just need to tell me the initial value of data and the final value of data. That's fine, right? So what is the initial value of data? Okay, initially you are up here at the North Pole, right? So then, of course, the initial value of data would be 0. And finally, after you're at the end point, so you're at the South Pole, right? So then at that point, your data value is pi. Right? So then this is the integration that you need to do. Integrate with respect to data. So now we take care of the integrand, right? So E dot data head. So E is something that we have just found, right? So as I told you, right, the E has two components. One is the R head component, the other is a data head component. So when you take this and dot product with this data head, right? So what you have is only the second term, right? Because R head dot data head would be 0. So you don't only need to care about the second term here. Okay. So therefore, the integral looks like this. So this one really is E dot data head. Okay. So now when I do E dot data head, so I also have this R variable here. So what kind of R should I be considering? So because as I said, right, so when I walk along this path, the R is always at capital R. Right. So that's why in the integrand, this small r really just kept as big R. Okay. So then the whole thing is actually quite straightforward now. So you are just integrating the sign data, the data, right? So all the other terms are just constant and can be taken out, right? So then if you go ahead and do it, what you find is 2qd divided by 4 pi epsilon naught r squared. Okay. So now let's consider the other path. Okay, the other path. So when I'm walking along this red path, okay, so this time, okay, so when I am talking about the dr, okay, so which coordinates not changing this time? So let me. So let me write down dr again. Dr is r head. Dr r head plus rd data head plus r sine data d phi head. So now if I'm walking along this red path, right? So this time, which coordinates is changing, right? It's the phi. And this time the r and the theta coordinates is fixed. Okay. So that's why when I consider dr, right, so again I don't need this term, and also I don't need this term. Okay. And here, so what should I take for r? Right. Again, I'm always, the r coordinate is always big R. Right? So what about theta? So here I told you already. So I'm staying at this theta equals theta naught. Okay, so that means this is theta naught. So then here I just put theta naught. So then that means really the dr is given by capital R sine theta naught d phi hat. Okay. So again, let's make sure that we understand the geometry. Okay, so if I really look from the top and draw the path, right, it's like this. Right, so and then we are walking like this. Okay. And let's say this is phi, right? And then this is d phi. So then the radius of this circle, right? So the radius of this circle really is this line here, right? And the length of this line is r sine theta naught, which is this one. Right? And here is d phi. So that's why this small arc length, right? So this small arc length, the length of this small arc, right, is this one, r sine theta naught d phi. And then you are going along this direction, right? So this direction is the direction for phi hat. So then this time, if I want to do the line integral, right? So this is an integral for phi. Right, so integrate e dot dr is actually integrate. Right, so e dot phi hat and then r sine theta naught d phi. So then again, you need to consider the lower limit and the upper limit, right? So lower limit, upper limit. So what is it? Is it because you are completing a full circle, right? So that's why it go from 0 to 2 pi. So now we need to take care of the integrand, right? So e dot phi hat, and actually is 0, right? Because the e does not have a phi component, so that's why this e dot phi is 0. So of course, if you, but some of you may have been recognized this in the first place, and then you realize that you don't need to do this integral at all, right? So, but that's okay. So here I just want to make sure that we understand how to set up the integration and the integration limit. Okay. So this one, right? So as I said, just 0, because this one is 0. So then from this problem, you can see that, okay, so in spherical coordinates, right? So these are two kinds of paths which are very convenient to do, right? Because in these two kinds of paths, you are only changing one coordinate only, right, at the time. And also, right, so one more is that although it's not in the exercise, but if you consider a line integral along a straight line which go from the origin all the way out to the surface of the sphere, this one will also be convenient to deal with, right? Because in that case, only r coordinate changing, right? And then the theta and the phi coordinate are not changing. Okay. So and then one quick question here, okay, just to check your concept that you previously learned. Okay, so can we figure out the result of the line integral without actually performing the integration? This case, asking you the same question, the value of this line integral, but without actually doing integration. Is it possible? So yes, why yes? You mean because it's the so are you saying that you are always go along the field lines? You are actually not always go along the field lines actually, because your path is more like this, right? So the field lines is actually not always parallel to you. So this one thing, okay. But do you remember last time we learned about conservative field? Is it a conservative field? Yes, of course, because we are deriving the field from the potential function. Right, so this is a conservative field. If it is a conservative field, that means the line integral, first of all, is path independent. And also, the value of the line integral is just equals to the difference between the potential value, right, of the endpoint and the starting point. So this is a electric potential, right? So that means all you need to do is that you take the potential value here and you take the potential value here. Okay, so let me call this point P, and then this is point Q. So last time when we learned about the fundamental theorem of line integrals, right? So the integral of the gradient function, right, from P to Q is equals to the potential value at Q minus the potential value at P. So this is in the first part of the chapter, right? So now we are basically doing this, right? So of course we are off by a minus sign, right? Because I'm doing minus gradient V instead of gradient V, but that doesn't matter. Let me just put a minus sign here, minus sign, minus sign. So that means this integral here is equals to the value of V at point P minus the value of V at point Q. So what is the value of V at point P? So at point P, theta and phi are all 0, right? So R is capital R. So at point P, at P, So this V is equals to 1 divided by 4 pi epsilon naught QD divided by capital R squared. Right. Whereas at point Q, V is 1 divided by 4 pi epsilon naught QD, again divided by capital R squared. The R value did not change, but the theta becomes pi. Right, so cosine pi, that's minus. So this, okay. So this one minus this one, which is exactly this. Okay, so that's the first part A and part B for this tutorial problem. Okay, so let's move on a bit on the lecture notes. Okay, and then we'll come back and do part C. Okay, come back and do part C. So towards the end of the lecture last time, so I started talking about the doing surface integrals and the flux integrals with this cylindrical coordinates or spherical coordinates, right? So and I introduced, okay, so the differential area elements for these two coordinate systems. Okay, so now let's take a look on how to use them, right? So first, let's talk about cylindrical coordinates. Okay, cylindrical coordinates. So suppose our goal, what is our goal? Our goal is that if I give you some vector field, right? So and then I want to find the flux of this vector field over some surface that we construct, right, in this coordinate system, right? So we are interested in finding this kind of integral, right? Flux. So okay, here so I draw 3 cylinders. Okay, so we are working in cylindrical coordinates now. Okay, so suppose I have these 3 cylindrical surface. Okay, so now if I want to find the flux, so suppose you imagine that so just consider the first case. So you imagine that the field, the F is in the space, but I do not draw the field here. I want to find the field. Okay, so through the curved surface of this cylinder, of this cylindrical surface, I want to find the flux through this curved part. Okay, so in Cartesian coordinates, so we have done this already. So but here we'll see that it's much easier to do it in cylindrical coordinates. So if you want to consider the flux, right? So we are, as I said, we are interested in knowing, in working this flux integral. So if I want to consider this, so I need to know how to write the n hat d sigma, right? So if I'm just considering the curved surface, right? So what is the n hat? But the n hat is the unit vector that is pointing normal perpendicular to this curved part, right? So and that therefore, of course, that is a vector that looks like this, and that is just rho hat. Okay, the rho hat in cylindrical coordinates. Okay, so let me try to draw the axis here. This is the z axis. Okay, let me draw it again. So the n hat in this case is just rho hat. Okay. And if I want to consider this whole curved surface, right? So the differential area element, of course, would be a little part, a little curved part like this, right? And this little part really exactly is this one. Okay. So that means we are taking this one as our n hat d sigma. Okay. So the n hat d sigma is rho hat rho d by dc. So now if I go to do this flux integral, right? So then that would be the field, whatever it is, so this is a double integral over phi and z. Okay. So how do we set the integration limit? Okay, first of all, one more thing. So what about rho here? So the rho here is the rho value if we are staying on this cylindrical surface, right? So then let me also, let's say that if the radius again is big R, right? So then the rho is just a constant value, this big R. Right? So then we have a double integral, right? So for phi and z. So how do we set the limit for phi? Okay. So again, if you are taking the full curved surface, right? So the whole cylindrical surface, then of course you need to complete one full circle. Then that would be from 0 to 2 pi, right? In that case. Right. So however, if you just consider part of it, right? So suppose I only consider, let's say this part of it. So then you need to consider two phi value. Right, so you need to consider the phi value for this line and the phi value of that line, and then put your lower limit and the upper limit. Right, let's say here is at phi naught, this one is at phi 1. It really depends on whether how much the curved part that you want to include, right, in your flux integral. So what about the z? The z, of course, is the z range of this cylinder, right? So for example, if here I have z equals z naught, and here is z equals to z1, right? The two planes, then here I'll go from z naught to z1. Okay. So this is the first kind of surface that is easy to do in cylindrical coordinates. Okay. So the second kind is that I consider the top part. If I'm going to integrate the flux, right? So just over this top circular area, right? So this time, what is the normal vector this time? The normal vector would be a vector pointing up, right? So of course, if you want to consider another one that's pointing down, that's fine. But let's say here, I define my orientation, okay, such that this I take this one as my normal vector. So in this case, of course, the normal vector would be z hat. So then the small differential every element, right? So would be this part. So if I look at this circular part, right? So then you are just thinking of polar coordinates, right? So if I'm doing this part here, right? So then I'm taking this part. So this time my area element is this. Okay. So this time n hat is z hat, n hat d sigma is z hat rho d phi. So then if I do the flux integral, right? So this time is taking the dot product between this f and z hat. Again, I will have the rho d phi. Okay, so this time the rho is not a constant, right? So you are considering different rho value, right? So depending on which part you are at on this plate. So in fact, if you are integrating the entire circular area, the circular region, right? So then of course your rho has to be just like what you do in polar coordinates. So it has to go from 0 to r, right? And then phi, right, in this case, because you're doing the full circle, is from 0 to 2 pi, right? But of course, you can just take part of it, right? You can take again like a slice of a pizza, right? So you can just take this part, for example. Then again, if this one is at phi 0, this one is at phi 1. Let's go from phi 0 to phi 1. Okay. Okay, so finally, if I want to consider a surface that is inside this cylinder. Okay, so you just imagine that you cut this cylinder, okay, exactly along this plane. Okay, along this flat plane. Okay, just cut it like this. So I want to integrate over this flat surface inside this cylinder. Okay, so in this case, again, how do we set up the ND sigma? So this time the sigma so would be the ND sigma would be this one. Okay. So this is basically it's the back surface of this small cube here. Right. So this one. So in this case, right, so the normal vector is pointing right into the plane, right into the plane. So it's a phi hat. Of course, if I take another plane, let's say if I take this plane instead. Okay, so then at this time my normal vector will be kind of pointing to the right. Right, so then the normal vector is like this. Right, so but in either case, right, so it's phi hat. Right, and the small area element is this one. Again, so if you do the double integral, right, so this time you are taking the dot product between your field F and the phi hat. Okay. So the rho, I go from, in this case, I go from like 0 to all the way to this edge. Right, from 0 to R in this case again. Right. Then the Z, of course, again go from here, Z0 to Z1. So that's the case for cylindrical coordinate. Right. So last time we also have this the three area elements, right, for this spherical coordinate. Okay. So again, let's see how it works. Okay, so again, we are interested to find this, right, the flux. So we want to consider the flux through this spherical surface. Okay, this spherical surface. Let's say the radius is R, okay, and this big R. So then what is the normal vector? The normal vector, right, so point out like this. This is, of course, R hat. Okay. And then the area of one small part, right? For example, this part. So that would be this part here. So then this is the one that we use. Okay. So then we are dealing with this integral. So if we're talking about this spherical surface, right? So then this R, this small R, okay, it's really just capital R squared, right? This is constant. So now, if I want to do the integration limit, so it really depends on, again, it really depends on whether you're considering the entire sphere, right? So, or part of the sphere, right? So if you're considering the entire sphere, again, you understand that this go from 0 to pi, and this is from 0 to 2 pi. Okay. However, for example, if I'm just considering this part, so then what do you need to do? But again, it's go from 0 to 2 pi for the smoothable angle, but for the polar angle, right, go from 0 to some value, okay, theta naught. And also, what about if I just consider this? What about if I just consider this? Right, so then the theta go from 0 and from the North Pole down to the equator, right? So then from 0 to pi divided by 2, right? And then what about the phi, right? So it really depends on the phi value here, right, and the phi value over there. So from phi naught to phi 1, okay, right, something like that. So now, another kind of surface that is easy to do in cylindrical, in spherical coordinates. Again, what I'm going to do is basically cut this. Let's say I cut this a sphere, right? Just like cutting a watermelon, right? So cut it like this, and then I want to know, right, let's say the flux through this half circle plane. Okay, right. So this red plane is the plane that I cut into the sphere. Okay, it's a flat plane. Okay, inside the sphere. Okay, so not on the surface. Okay, maybe the picture is not very good, but this plane is inside. It's the flat plane inside. So then in this case, again, what would be the normal vector? So the normal vector will be the one that is pointing into the page. Okay. So then basically we are considering this the back face of this element here. Okay. So we are using this one. Okay. So then if we do the flux integral, so we are taking f dot phi hat, right? And r d theta. So the r limit go from 0 all the way to the surface of the sphere, which is capital R. But if I really consider this full half circular plane, right? So then it really go from 0 to pi. again, however, if you just consider like this part of it, this green region, okay, and this angle is theta naught, then your integration limit for theta is go from 0 to theta naught. Okay. Okay, so now let's take a break. Okay, let's take a break. I'll show you two more example, and then you work on part C in the tutorial problem. Okay, part C in the tutorial problem. Okay, so let's look at two examples. Okay, one is for the flux in cylindrical coordinates, and then the other one is for flux in spherical coordinates. Okay. So here I give you a vector field. Okay, so this vector field expressed in terms of cylindrical coordinates. So rho phi z. Okay. So then I have this surface of this cylinder. Okay. So I want to find the flux, okay, through this cylindrical surface. Okay, I want to include every part of the cylindrical surface. So the upper part, the lower part, and also the curved part. Okay, I want to find the flux, okay, through all the parts of the surface. Okay, so in this case, right, so I'll consider three integrals. Okay, so the integral over S1, so which is this flat circular plane, and then the middle one, of course, the curved portion, and then finally the bottom one. Okay. So when I find the flux through this closed surface, remember the convention is that I always want the normal vector to be the one that is pointing out of the region. Right. So then that's why if I consider S1, the normal vector is z hat, okay, pointing up. For this curved part, S2, right, so rho hat. And for S3, okay, so this time it should be minus z hat because I'm all finding the flux outwards. Okay, so all the normal vectors I pick are pointing out of the region. So there are three integrals to take care of. Okay. So first one, right? So the one that is for the S1. So I just use the same thing that I talked to you about, right? So this one here. And then the second one, which is the curved one, so this one here, right? So again, it's the same treatment as what I have just told you here. And finally, this one, okay, the third one is very similar to the first one, but now you need to make sure that you have the minus sign here. Okay. So then here I need to take care of the integration limit, right? So here I have this radius, again, this radius of this cylinder is r, right? So whenever you have this integration for this d rho, then it's go from 0 to r. Okay. And then I consider the complete the whole thing, right? So you need to go the full circle. Then whenever you have this integration for phi, you go from 0 to 2 pi. And then from z, okay, just go from this z value to this z value. Okay. So here I told you that the height of this cylinder is h, okay, and the standard origin. Okay, so that's why my z limit go from minus h divided by 2 to h divided by 2. And then I take care of this dot product for the integrand. Okay, so they're all here. And one thing to notice is that when I do the integral over S1, so whenever I see the z variable, I just put z equals h divided by 2. And then the second integral, whenever the integrand show me some factor of rho, right? So I just put rho to be this capital R. Right? And finally, in the last one, if I have this z variable in my integral, okay, I just put this z equals to this constant minus h divided by 2. Okay. So make sure that you understand all three terms. So they are using these three cases, okay, respectively. I'm sorry, not all three cases, actually, just this one and this one. Okay, we didn't do the third case, actually, just this one for the curve, right? This one for the upper and the lower, right? With respect to these two cases. Okay, and then the second example, which is the flux through the spherical surface. Okay. So I'm sure that maybe you are learning, or you will, or you have learned about Gauss' law, right? So you find the flux of electric field. So one typical situation is that you want to find the flux through a closed spherical surface. Right? So here I have a slightly more complicated field. Okay, not electric field, but some vector field. Okay, so and then I want to find the field, right? The flux through this spherical surface S. Okay. So this time, because I am doing the spherical surface, right? So then this d sigma that I use, right, would be this case here, right, which is this case. So then the f dot n, right, just f dot r hat, and then you just actually do the dot product, and then the integrand will depends on all r, theta, and phi. Okay, but again, because we are talking about a spherical surface, so that means the r is a constant value. The r is capital R, which is the radius of the sphere, and at the end you get the answer here. Okay, so now let's try to do one problem by yourself by looking at part C of the tutorial problem. Okay, so again, we are just using the same electric field in part A. This time, I want you to find the flux of this electric field through the upper hemisphere of this spherical surface. Okay, not the entire sphere, but just the upper part. Okay. Okay, so to find the flux through the upper half of this sphere, right, so we are considering this part of the surface. So the ND sigma that we take in this case, of course, is this one. Right, so this is a double integral that we are going to do, and the limit, the phi limit, okay, the whole part of the northern hemisphere will also will go from 0 to 2 pi, right? But for the polar angle, it just go from 0 to pi over 2. So, and what is E dot R? Right, so E dot R, this part, this time, right, just the R component. The R, we just consider the R component of E. That is right. So this whole thing is E dot R hat. So now we have some R variable in the integrand. So remember that we are staying at the spherical surface, right? So the R really is big R. Okay. Then I can just take out the common factor. Right, so take out the common factor. You have this QD. Right. This. So the integral for phi is just give me a factor of 2 pi. Right. So and then integrating this, right, just equals to, right, this one is just integrating from, right, just integrating sine theta d sine theta, right? So this inner integral actually just 1/2, okay? And the outer integral gives you a factor of 2 pi. Okay. So then the final answer would be this one. So what about the flux through the entire spherical surface? What about through the entire spherical surface? So of course, mathematically, you know that you are just going to change your integration limit, right? Instead of pi over 2, you just change it to pi, and you see 0. Okay. But let me test your physics. So why is it 0? This is an electric dipole. Right. So Gauss law, right? So you have learned Gauss law. So that's the physical reason, right? So considering electric dipole, positive charge, negative charge, total charge 0. So flux through the spherical surface is 0. And you know that since you have learned Gauss law, you also understand that even if I don't choose a spherical surface, right? So another shape, as long as the surface is enclosing the dipole, right? So then the flux that you get should also be 0. So although if you take other shape for the surface, the integration may be easier, may be more difficult. Depends. Okay, but I will say a few words about Gauss law in later in this chapter. Okay. Okay, so that's so much about doing gradient line integrals and this surface and flux integrals in these two different coordinate systems. Okay, so next, let's also take care of the divergence and the curl of the vector field. Okay. So here I don't have much to explain. Okay, what other than showing you the formulas. Okay, so in Cartesian coordinates, so the divergence is given here. Okay, so in cylindrical coordinates, okay, the divergence, okay, will be looking more complicated. So just like the when we talk about gradient, right? So the gradient in cylindrical coordinates and the spherical coordinates will look more complicated than the Cartesian coordinate case. Okay, but again, once we have a situation where the function itself is take a simpler form in one of these two coordinates, okay, compared with the Cartesian coordinates, then we will have the advantage. So I'm not going to, the proof is beyond the content of this course, but if you want to see here, for example, you can go to this book here. Okay. And in fact, I think in your if you have that book of Introduction to Electrodynamics by Griffiths, okay, so I think in the appendix, okay, so it also shows a proof on how to get the formula for divergence in different coordinate systems. Also curl. Again, I don't have much to explain, okay, rather than just showing you the formula. Okay. So when okay, so but I hope you remember this formula, okay, but not necessarily the formula for the other two coordinates, okay. So same thing here, okay. So at least remember the curl of f in Cartesian coordinates, okay. Okay, so now so as I said, I don't have much to explain for these two items, so I can give you a vector field, and then you just follow one of these formulas to take the divergence or curl, right, depending on the coordinate systems we are talking about. So here, let's do again one example. Okay, so I have a vector field. Okay, so and I want to find the integral of the curl of v dot n. So what we are having is the following, right? So again, what I have here is, first of all, a coordinate system, right? And then I have a hemisphere. Okay, a hemisphere. Okay. So this vector field V, okay, is everywhere in this space, and I just don't draw it. But if you take the curl of V, right, so curl of V itself is also a vector field, right? So, and then I want you to find, so let's say right, so if I just take this part of the surface, so it has its own, again, n vector here, and then also over here, you can find the curl of V. I'm not sure whether the curl of V is pointing this way or not, but this is a curl of V, right? So I want you to integrate. So basically, this is the flux of curl of V, right, through this upper hemisphere surface. So I want you to do this surface integral. So here, because I'm asking you to integrate over a hemisphere, you expect that it'll be easier to use spherical coordinate, right? So when we do the integral. Okay, so but one thing is that, however, I give you the vector field in Cartesian coordinate, right? So one thing is that, okay, so do we want to change all the field to the spherical coordinates also, and then do things, or if we just simply take the curl of V first, and then in Cartesian coordinate, and then convert that to spherical coordinate. Okay. So in fact, in this case, if I just look at it, I will see that it will be quite a bit of work even to convert this field in spherical coordinate to begin with. Okay. So first of all, okay, so I should mention that this ijk just means x hat, y hat, z hat. Right? So then what I would do is just to simply, first of all, just take the curl of V. Okay, so in Cartesian coordinate first anyway. So just take the curl of V first, just to see how it looks. And of course, you can work out all the details, right? So, but I'll just give you the answer is -3 V hat. So actually, this field is quite simple. Okay, so it's just always pointing in z direction. Oh, actually, it's negative z direction. Negative z direction. So now, if I want to set up the integral, right? If I want to set up the integral, if I in spherical coordinates, right? So I will have this double integral. Right? So again, I will have 0 to pi/2. Right? Again, just half of the sphere. So, and really, this R again is we just replace it with the radius of the sphere, this time, which is a. So this one is just a squared. So then we just need to take care of this dot product. Okay. So here we have the dot product in for z hat and r hat, but one is in Cartesian coordinates, the other is the spherical coordinates. Okay, so but this one actually, if you still remember the picture, the geometry, it would be actually easy to figure out, right? Because you know that the z hat is always pointing up like this, and the r hat is a vector that looks like this, and the angle, right? The angle between r hat and the z-axis is always, right, just the polar angle theta. Right. So that's why z hat dot r hat is simply cosine theta, right? And that theta is the theta in the spherical coordinate. Right. Right, so that's why this one is -3 cosine theta. If you go ahead and do this integral, right, it's very similar to what we have done already. Okay. So this is the flux of this curl V, right, through this hemisphere surface. But remember, by Stokes theorem, right? So there's another way to do it, right? So this is by Stokes theorem, right? So this one is equals to this line integral. And C is this path. Because the C forms the boundary of the surface, right? So then you can also try to do this line integral, right? So instead of actually doing this flux integral, okay. And remember, right? So if you don't quite remember Stokes theorem, right? So remember that the line integral, right? So over a closed path is equals to, right, the double integral of this flux of curl of V over any surface enclosed by this C. Right? So if I pick another surface, like this, but this surface is still, right, the boundary is still given by this C. Right? So then this is still the same. So the flux of curl of V over this yellow surface is the same as the flux of V over this purple surface. Okay, and then next, I basically here I just list out some vector identities. I know that in your homework, you are actually need to prove, I think, one of them. Okay, I think in your homework problem, right? So I think you are working on, I believe it's this one, right? So but these are the thing that you can prove just using algebra, right? So you can see that, for example, the first one looks like the sum rule and the product rule and so on. Okay, so all these vector calculus identity can be worked out, right? So by just really considering the derivatives term by term, and using the sum rule and the product rule for differentiation. Okay, so all this, of course, I don't really expect you to remember all of them, but as you can see here as a practice, I give you one of them to work on in your homework. Okay. More comes here. Okay, so in this page, okay, so it only involves the first derivative, okay, or the identity. Here involve the second derivative. Okay. So I think I only have a few minutes left, but I would like to try to talk about just a few more remarks before we end this chapter. Okay. So remember we have learned about Green's theorem or Stokes theorem, right? So we take the line integral, right? So along this path C will be equals to the double integral, right, over the double integral of the circulation density over the region inside the curve. So, but we have been just considering this region, okay, without any holes in it, right? So this first upper part of this line, okay, is what we have been considering, a curve bounded by this region. So the region bounded by this curve. So now, what if I want to consider a region like this? Okay, it has a hole in it. So that means it has an outer boundary, which I call C1, and an inner boundary. Okay, the boundary for this hole, C2. So in this case, the Green's theorem will look like this. Okay. So in the original case, right, so we just do this line integral, which is the left-hand side, will be equals to this double integral, right? So integrate of this circulation density over the entire area. So here, if we have a hole, okay, in the region, then, okay, the right-hand side the same, is still the double integral over the region, but of course excluding the hole. And then the left-hand side becomes the sum of two line integrals, which is the line integral over the outer boundary plus the line integral over the inner boundary. Okay. But when we do the line integral over the inner boundary, we do it clockwise. So by convention, we always do this line integral over the closed loop counterclockwise. Right? So, but in this case, okay, so the Green's theorem becomes this. Okay, the sum of two line integrals. The outer boundary, do it the usual way. Okay, the counterclockwise, but then the inner boundary, do it clockwise. So how does it work? So why is it like this? Okay. So there's a very simple geometrical proof. Okay. So when we talk about a region with a hole like this, okay, so we can actually consider this one and then cut it in half. Okay, cut it in half. So here I have two regions again, but if I consider each region individually, it is a full solid region, right? So no any hole, right? So this one does not, I don't consider this one as a hole anymore because this whole region itself can still be bounded just by one loop, right? So one region with a hole divided into two become two regions, okay, without any hole. So now, if I want to talk about the line integral, Okay, so the line integral that encloses this A1, okay, so that would be equals to the line integral that enclose A11, right, the left subregion, plus the line integral that enclose A12. So then the question is, so what does it mean by the line integral that enclose A1? So I'm treating this one, these two as this one as the definition. Okay, so the definition of this line integral enclose A1 is defined by the line integrals enclose A11 and the line integral that enclose A12. So now, if I want to consider the line integral that encloses A12, A11, and A12, so what I need to do is to draw these two boundaries. Right? So I call this C11. You can see I have this one, C11, and then the line integral that encloses A12 is this curve, right? C12. So now, if you try to bring these two regions back together, okay, again, considering the line integral and to see which part cancel, you can see that this line integral here cancel this part, this line integral here cancel this part. Okay. Then that means the line integrals that encloses A11 plus the line integral that encloses A12 would be equals to this big line integral out there plus this small line integral inside. And you can see that this line integral inside, okay, just follow the arrow, right? So they are doing clockwise. And that's why it can be treated as two separate line integrals. Okay, one is this one outside, okay, counterclockwise. And the other is this one inside, clockwise. Okay. And now, if I just consider the left subregion, like A11, right? So the Green's theorem give me this term. And then if I just consider this subregion A12, right, the Green's theorem give me this term. So now, if I just add this and this, right, so that would be the double integral of this flux density for this entire blue region. Okay. And that's why the Green's theorem is modified like this. Okay, so whenever you have the hole, okay, you need to add one more line integral, okay, for the inner boundary. And that inner boundary, when you do it, has to do it clockwise. Okay. And you could imagine that this argument can be generalized with 2 holes, 3 holes, so on. Okay. Okay, so I'll stop here for today. Okay.